And green is bad, so
Yeah, green is the bad. Yellow.
there needs to be a little flashing yellow light. Like that. You see, that's good.
Okay. Yeah, I see it's yellow.
So maybe I'll ask you in a couple of minutes to check again.
You were allowed to use the fast track on the visualization.
Yeah? Cool. Thank you.
Oh, I mean, was that the question?
Yes.
Yeah.
City car
Sorry.
share.
I thought
We're on the bridge. I was like, wait a minute.
No, you guys said.
Oh, but I don't know if it's the city car share one that.
On their website.
Oh, cool.
They say you're covered on their team.
Nice. All right, so Hopf algebras. Finally, this is not the topic of the semester. This is the topic of the day. So we finally got to the point of defining Hopf algebras, and this took a little bit of building up. So first we defined what an algebra was, then what a coalgebra was, which was kind of a dual object to an algebra. Then we defined what a bialgebra is, which is something that is both an algebra and a coalgebra, and there's a compatibility between the algebra and coalgebra structures. And finally, we can define what a Hopf algebra is, and I did it last time. It's a bialgebra with a little bit of extra structures. So Hopf algebra H is a bialgebra with an antipode. It's a linear map. From the bialgebra to itself, such that this diagram commutes. And the diagram says, you start with H, you apply the coproduct, okay? Then you apply the antipode on the left and the identity on the right. And then you apply the product. Okay. Or I can do the same thing, but applying the identity on the left and the antipode on the right. And then the product. And I should get the same going this way or this way. And also I have another way of going from H to H, which is to go through my ground field by using first the co-unit that sends H to the field, and then the field to H using the unit. Okay. So this is the commutative diagram that you need for a Hopf algebra. Okay. Plus, you need to check all the other properties of being a bialgebra, which, as you now realize, is a lot of things. Okay. And so I thought maybe what I would begin by doing today Give me a second. Okay. Hopefully the camera is going to be good. So this is the definition, and what I want to do is begin by just discussing a few examples of what this antipode looks like in some of the bialgebras that we have seen, or in some cases maybe it is impossible to have an antipode. Maybe you have a bialgebra and there's just no way to put an antipode on it. That's another possibility. So we're going to do a bunch of examples. Okay. So our first example is going to be a group ring. Okay. And give me a second. Let me just check and make sure that the camera is still on before we get too carried away here. Okay, that looks good. Yeah, I think it's okay. It's kind of a sophisticated algorithm, actually. The way that this thing follows me around, there's a little bit of a delay, and it's smart. So supposedly, the algorithm is supposed to point to the right place if I do things right. So hopefully that's true. So we saw over the last couple of classes that if you have a group and you consider the group ring over a field, then that has a bialgebra structure. Okay. And so now the question is whether you also have an antipode, which is going to make this into a Hopf algebra. Okay? And so what we need to do is, well, just see if we can define an antipode, right? And so given that the antipode is supposed to be a linear map, I just need to define it on a basis. And here we have our basis given by the group elements. Okay. And so let's just see if we can pull this off. So we need this diagram to commute. And again, if we want to check that this diagram commutes, we need to, there's three ways of going from here to here. And we need to check that the three coincide for every element here. But given that everything is linear, we can just do it for basis elements. And so let me just check it, start with a basis element here and see what needs to happen. Okay, so I take a group element G. Okay. So if I apply the coproduct, remember that here the coproduct is just G tensor G. Then I apply the antipode on the left and the identity on the right. Okay. And then that takes me to S of G times G. Right? It's important that I keep track of the order because this is not necessarily commutative. If I go down this way, I get basically the same thing but backwards. So G tensor G, then this goes to G tensor the antipode of G, and then this goes to G S of G. And finally, if I go this way, remember that in the group ring, the counit sends every basis element to 1. And so this goes to 1, and then the unit takes the 1 of the field to the element 1 of the group. Right? So maybe I'll put it kind of bold here. Or maybe I'll just write 1 sub G. So remember that that's supposed to be the 1 of the group. Okay? And so if I'm going to be able to define this successfully, I need to make sure that these three things are equal to each other. And so you see what I need to do. Right? So the answer is that I should define the antipode such that S of G is both a left and a right inverse of G in the group. In other words, the antipode just sends me to the inverse. The antipode of G is G inverse. Okay? So, and this sounds like an antipode. So, let me repeat something that was mentioned last time. That we have this other meaning of antipode, which is that if you're in the globe and you're standing somewhere in the globe, then the antipode is going kind of to the other end and then coming back. And that intuition is kind of reasonable here in that you're going from a group element to the inverse and back. There's no sense of going really far and back because for example, S of 1 is 1. It's not that, but at least it's true that S squared is equal to the identity. Right? S of G is going to be G. And I also mentioned last time that you can think of this antipode as something like an inverse, an analog of an inverse, and so this makes this a little bit more precise in that if your bialgebra is the group ring, then this is exactly the inverse map. Okay? All right. So are we happy with that example? Any questions about it? So let's do another example. But actually, maybe before I do that other example, let me remind you of a question that Seth asked last time. Is it true that S squared is always equal to the identity in any Hopf algebra? And we don't have too much evidence right now, but so far the answer is yes. So far, at least in this family, S squared is equal to the identity. Let's do another example. So let's try to take this example of the last two homeworks. So H4 is as a vector space is generated by 1 gx and gx, but we impose some additional relations. We say that g squared is equal to 1, x squared is equal to 0, and xg is equal to minus gx. And so this defines the product here. And the coproduct is given by this. Okay. And as you realize by thinking about the homework, you realize that maybe at first it wasn't obvious that. I mean, in the first homework, I asked you to check that this is an algebra and prove that it's four-dimensional, etc. And maybe that wasn't obvious immediately, but you checked that this does define an algebra. And in this homework, you're checking that this does define a coalgebra. And in fact, those are compatible, so this really is a bialgebra. So the question now is whether this bialgebra is also a Hopf algebra. And so we just need to check if there's an antipode. Okay? And so let's do the same thing that we did over there. We need to check. We need to if an antipode exists, then it has to satisfy several properties. And so what we're going to do is we're going to chase the diagram around, starting with a basis of h. So we need to do it 4 times, one for each element. Okay. So maybe the easiest element is 1. So if I start with 1, then what is delta of 1? Well, so this is something you realize in the homework, that I didn't tell you what delta of 1 is, but if this is to be a bialgebra, then delta of 1 has to be 1, because delta is supposed to be an algebra map. And 1 in the tensor product is called 1 tensor 1. Okay. Then this goes to S of 1 tensor 1, and you multiply them. Okay. If you go around this way, you're going to get the same thing but backwards. So this also goes to S of 1. And if you go this way, oh, I guess I forgot to write down what epsilon is. So the co-unit was given by 1 at g, 0 at x. But again, it's implicit that because else epsilon is supposed to be an algebra map, epsilon of 1 has to be equal to 1. So 1 goes to 1. And the unit of 1 goes to 1. Okay. And so here I'm getting 3 answers, and they need to be equal to each other. In other words, I should define S of 1 equal to 1. It's the only thing that S of 1 can be. Okay. All right. Now let's do it for G. I think G is the next easiest because this is an easier formula. So G, I take the coproduct, and that takes me to G tensor G twice. Okay. Now I apply S on the left and on the right. And so this is going to take me to S of g times g. This is going to take me to g S of g. And if I go this way, then g takes me to 1, which takes me to 1. Okay? So these three things should be equal to each other. So what should I define S of g to be? You don't quite want to write G inverse, because this isn't a group. But G squared is equal to 1. And it's easy to check, actually, that if G times something is equal to 1, then that something has to be. I mean, if S of G is a left and a right inverse for G in here, then it's easy to see that that's actually unique. That's true in any algebra, that if you have an element that has a left and a right inverse, then that left and right inverse is unique. That's an easy exercise. And since G is a left and a right inverse for G, then S of G has to be G. Good. So that's good so far. Now let's do it for X. So X takes me to X tensor 1 plus G tensor X when I apply the coproduct. Okay. Now let's apply S on the left coordinate. Okay. And the identity on the right. So here I get S on the left coordinate and 1 plus, now S on the left coordinate is, so I get S of G, but I know what S of G needs to be. S of G should be G. Okay? So let me just make a note to myself that here I already plugged in S of G. Okay? And so this goes to S of X plus Gx, right? Now I go this way. I get to apply the antipode on the right-hand side, so I get X tensor S of 1, but S of 1 is 1. Right? So here again, I'm plugging in S of 1 plus G tensor S of X. And when I apply the product, I get X plus G S of X. Right? And now I go this way. So X maps to 0, and 0 maps to 0. Okay? So I need these three things to be equal to each other. Okay? So that means that S of X should be equal to what? Well, according to this, S of X needs to be minus Gx but here you see that something could go wrong, because this equation is also demanding something. And so if S is going to be well defined, then this thing better be 0 also. So is that true? X plus G times minus Gx. Well, luckily G squared is equal to 1. And so let me write it down. X plus G times minus Gx. G squared is equal to 1. And so I get X minus X, which is 0. And so that means that these two equations are compatible and have a common solution. Okay? But here you start seeing how it's possible that S might not be well defined. Here we got a little bit lucky, because it could be that these two equations were inconsistent. And if they were inconsistent, then we could not make it into a Hopf algebra. Okay. Let's do the last one. So we start with Gx, and we apply the coproduct. Now, again, even though I didn't write delta of Gx for you here, because delta is supposed to be an algebra map, you know that delta of Gx has to be this times this. So let me multiply those things. I'm going to get Gx tensor G plus G squared, which is 1, tensor gx. Okay? And here, same thing. Gx tensor g plus 1 tensor gx. Okay? Now, I apply my antipode on the left side. I don't know what S of gx is, but I know what S of 1 is. S of 1 is 1. Here I apply it on the right. So gx tensor S of g, which I know is equal to g, plus 1 tensor S of gx. Okay? And then I'm going to get here, when I apply the multiplication, I get this. Here I get gxg plus S of gx. And finally, if I come across here, what do I get? Well, again, I didn't tell you what epsilon of gx is immediately, but I kind of did tell you because I told you this is supposed to be a bialgebra, which means that epsilon of gx has to be 1 times 0, which is 0. And the unit of 0 should be 0. Okay? And so that tells you what S of gx needs to be. We just need to figure it out. So what is gxg? Gxg is equal to xg is equal to minus gx, and g squared is equal to 1. And so this is just minus x. And so the second equation wants S of gx to be equal to x. Okay, but again, we need to cross our fingers and hope that this other equation is also true. Is it true that xg plus gx is equal to 0? It fortunately is true. Xg plus gx is equal to 0. That is true. Okay. And that means that these two equations are consistent and have a unique solution, which is this one. Okay. And so there you have it. The diagrams forced upon us what the antipode needed to be, and the antipode worked out to actually be consistent. Okay. It is well defined. It is linear because we just defined it on a basis, and then we need to extend it linearly. And it does satisfy all the commutative diagram because it satisfies it for the basis elements. So this actually makes it into a Hopf algebra. Okay. Yep.
So here we see that how basic is tough, like as just as a permutation on these 4 basic elements. Right? Is there any way, say we have S on 2 different basic elements? I mean, and producing the same thing, yet S still makes it other as an antipode. Is it possible?
So your question, as I understand it, is basically, I mean, in this example, and also in that example, we see that S is actually just a permutation of the basis. And so, can you say that that's true in general? Can you say more things? And the answer, whether that's fortunate or unfortunate, is that that is not true. So here we just happen to have some very nice bases, and the antipode happens to behave very well with respect to those bases. But in general, the antipode is just some linear map, and there's no reason why I should just permute the basis. S of gx is equal to, what did I say? X. Okay.
So in this case, the question of is S squared equal to the identity is not true because S squared of X is going to be negative X.
That's right. And so we get an answer to our question, which is no. And I should tell you that this answer took a while to discover, in that this example took a while to discover. But I wanted to show it to you because this is an example where S squared is not the identity. Right? S squared of 1 is 1, S squared of g is g, but S squared of x is minus x.
Out of curiosity, since you brought it up, how does one go about discovering a structure like this? I mean, it seems like there's so much order on these things. Like, how does one construct a Hopf algebra?
So give me Give me just a second. I'll address that question, but let me just make a point here, which is, let me make an observation that even though s squared is not equal to the identity, s to the something is the identity. One reason we know that is that, as Sam is observing, s is just a permutation. And we know that any permutation of a finite set has a finite order. So what is the order of this permutation? S has order 4 in this Hopf algebra. So the S of 1 is 1, S of g is g. Now, S of x, let's apply S to the element x. So apply it once, you get minus gx. Apply it twice, you get minus x. Apply it 3 times, you get gx. Apply 4 times, you get x. So S to the 4 is x. S to the 4 of x is x, and S to the 3, S to the 2, S to the 1 are not. And similarly, S to the 4 of gx is gx. And so in this example, S has order 4 in this particular Hopf algebra. Yeah?
So so do we have, can we generalize this S squared equals I to S to the n to some finite n? Is this possible with the dimension of the Hopf algebra?
So let me give you the answer to your question, which will be part of your homework 3. By the way, homework 3 is already posted. The answer is that there is no Hopf algebra that has odd order, for which the antipode has odd order. So the antipode cannot have order 3, it cannot have order 5, it cannot have order 7. But there exist Hopf algebras where the antipode has any even order. And so in the homework, you will verify that a certain Hopf algebra has antipode of order exactly 2n. And you will also find another one which has infinite order. And those are all the possible orders that the antipode can have. 2, 4, 6, 8, etc., or infinity.
Is there a rule about the orders, about the dimensions of Hopf algebras, that they must be even or odd? Or maybe arbitrary?
The question is whether there's something about the dimension of a Hopf algebra. And let me give you a cheap answer, which is that here's a Hopf algebra that has dimension equal to the number of elements of the group. And since there are cyclic groups of any finite order, that means that there's Hopf algebras of any finite dimension. Zach's question, how do you come up with Hopf algebras? Well, one way of discovering Hopf algebras is to discover them before the subject has been invented, which is what Hopf did, or what other people did. They just found these objects. And then the theory of Hopf algebras was created to fill a need of kind of analyzing the structure of these different objects that look similar to each other, and this was the structure they have in common. And so the theory of Hopf algebras starts already with a range of examples of what they're meant to model. Okay, one challenge of teaching this course at this level is that I can't assume that you know Lie groups. I can't assume that you know Lie algebras. But actually, a lot of the classical examples come from Lie groups and Lie algebras, and they motivate some of these constructions. Okay, and for example, you already realize that it's kind of a pain to check that something is a Hopf algebra by hand. But there are general constructions that, for example, something called the enveloping algebra of a Lie algebra is a Hopf algebra. And so that's a theorem that you prove in a very general setting. And then you get a lot of particular examples that come out of it. And then you kind of write down explicitly what they are for small values, and then you get some ideas of what these things need to look like. But I should say that, it's a non-trivial thing. And for example, in the homework, you will see a Hopf algebra of order 2n for any value of n. And that was an open problem for a long time, whether there existed Hopf algebras of any finite order, any even finite order. And it took a while to come up with examples, but now we have an example, and it's in your homework. Now we understand it well enough that it can be a homework problem, but at the time it was hard. Okay. So So that's, well, let's see. Let's see how I'm doing for time. Let's do a couple more examples. Well, let's not do this example. Here's an example we're not going to do. What if I consider the bialgebra of posets that we discussed last time? So isomorphism classes of posets with a bottom element and a top element. Okay. So we saw that's a bialgebra. We proved it last time. Is there an antipode? Okay. So here you see that's a trickier question because the basis is a little bit more complex, right? And so, you know, if you wanted to figure out whether there's an antipode, you would basically have to do this diagram for every basis element, in other words, for every poset, or every isomorphism class of a poset. Okay. So it's a little bit more complicated, but I mean, it's not impossibly complicated. And again, you know, it's at the right level of difficulty that I can give it to you as a homework problem. So that's what I did. So that's so the answer to this you will know in 2 weeks. Homework, 2 weeks or sooner. That's all. That's a homework problem, and this will give you an idea of how to approach that problem. Yeah.
So,
Well, I am listening, but let me check on the camera again. I just want to be sure. So go ahead.
yeah, so I mean, look at this, like, for example, basically, like, check all the specific, I mean, about the existence of an antipode. So is any characteristics in the structure of any of these that might actually give us some proof? I mean, like it.
So your question is basically, as I understand it, you know, okay, so this is kind of hard to do by hand every time, right? And so is there some general theory that tells me there is an antipode or there's not an antipode, or is there a general formula? And we'll see. We'll see that in some circumstances. And one thing that I mentioned is that in every classical example that got the field started, there is an antipode. And we will prove theorems of the sort that if your bialgebra is nice enough, then you have an antipode, and the antipode is given by this formula. Okay? But in general, that's not true, and in general, that's actually a very interesting question, and you know, people, including myself, write papers about this, where what people do is find the antipode of a Hopf algebra, which wasn't known to have an antipode, or maybe the formula wasn't known. Okay? So this is, I mean, in some cases it can be a tricky question. Okay, let's do another example. Let's do now not a group ring, but the bialgebra that we constructed from a monoid. Okay. So we said, for example, let's do it for the particular monoid of subsets of a set, okay, where we said that the product, so given two sets A and B, their product is their intersection, and the antipode of a set is, the coproduct. The coproduct of at a set is just the set tensor itself. Okay. So let's try to figure out what the antipode should be. So we do the same thing. Let's start with a basis element A. Okay. So apply the coproduct, and we get A tensor A. Then we apply the antipode on the left. We get this. Okay? And then we get S of A times A. Okay? But if we go this way, then I didn't write it here, but this is equal to 1. Okay? And so here we get the number 1. And then the element 1 of the field goes to the 1 of the monoid. Okay? So let me write it like this. U of 1 is equal to the 1 of the monoid. And what is the 1 of the monoid? So who has the property that when you that A intersect it is always equal to A? The whole set, right? Yeah, that's a great motion. So let's say that the set is called T. You don't want to confuse it with the antipode. So these are the subsets of T. We intersect them, and so the 1 of that monoid is the whole set T. Okay. And so 1 goes to T. Okay, so this should be equal to this. Okay, so what should we have here? S of A is just a combination of subsets, right? Let me write it. So S of A, given that S is a linear map from here to here, S of A has to be some linear combination of subsets. Let's say from I equals 1 to K, I don't know, where the AIs are subsets of T. Okay? So what is S of A times A? What we do is that we take the same combination, but we intersect everything with A. And supposedly this is going to equal T. Is that possible? Well, here the subsets of T form a basis for this space. So the right-hand side is just a basis element, and this is supposed to be a linear combination of basis elements. And so actually, all of these coefficients have to be 0, except for one that has to be equal to 1. And that guy has to satisfy that AI intersect A is T. Is that possible? T is the whole set. A is a subset of it. When you intersect with something, it's going to give you a subset of A. Right? So this is a subset of A. And so you're not going to be able to get a T if A is a proper subset of T. Give me just a second. So impossible for A different from T. If A is a proper subset of T, then everything that you're going to get here are proper subsets of T, and you're not going to be able to pick up a term T. And therefore, the antipode does not exist. You just cannot do this. Antipode does not exist. So there's no way to turn this into a Hopf algebra. Question?
Okay, so just to clarify, so what the subset of A, you're just saying that the intersect of some A sub I with A is a subset of A, or are you saying that whole thing, which is the sum?
So I'm saying S of A is a linear combination of sets. When I multiply by A, what I have to do is multiply every one of these guys by A, in other words, intersect it. And so I get another linear combination of sets where the sets look like this. And so what I'm saying is that each one of these sets is a subset of A. And therefore, none of them can be equal to T, which means that this equality cannot hold. And that shows that the antipode cannot exist. And so this is good to see something that is a bialgebra, but there's absolutely no way to turn it into a Hopf algebra. cannot do it. Yep.
Do we mean order of G equal to T?
No, so maybe I should have said this, but well, I definitely should have said this. This is notation for subsets of T. So to do the set is the power set of T, subsets of T. Okay. So I hope that gives you a better picture of what this antipode is about. And I don't know. I like it. I think this is more fun than checking algebra by algebra. You're actually kind of computing things and seeing some concrete things happen. I think this is kind of fun. Okay. That's a great question. So given a bialgebra, is it possible to have more than one antipode? Is it possible to give two different Hopf algebra structures to the same bialgebra? You actually anticipated the next thing I was going to do, which is to prove that that's not possible. Oh, but I realized I had another quick example. A lot of examples today. The polynomial ring. The polynomial ring we saw is a bialgebra. And I want to define an antipode. And I claim that I can. And the antipode is defined like as follows. The antipode at x to the n, which is one of the basis elements of here, is going to be minus x to the n. Which again sounds kind of antipodal. So let's check that this is indeed the case. Let me start with the basis element x to the n. So now I apply the coproduct. And so you have to remember what delta of x to the n is. Do you remember? The sum, and choose k, x to the k, tensor, x to the n minus k. So now we apply the antipode on the left. And so I get sum of n choose k. Now x to the k becomes minus x to the k. And this guy is intact. Okay. And then I apply the product. Something bother you? So all I did is s takes x to the k to minus x to the k, and now I apply the product. Okay, and the product tells me whenever I see a tensor, I should multiply. Okay, and all of these sums are for k from 0 to n. And I hope you recognize this. So this is just the binomial expansion of minus x plus x to the n. Okay. So how much is this? Two cases. If n is greater than or equal to 1, then this is 0 to the something. 0 to the something positive is 0. But if n is equal to 0, it's actually 1. It's one of those things. What is 0 to the 0? Well, instead of taking it there, just look at the sum. And you'll see the sum has only one term, and that term equals to 1. And we'll spare ourselves the 0 to the 0 debate. Okay. 0 and 1. Okay? You can imagine that if I go the other way, I get the same thing, right? The only thing is that here I get x plus minus x to the n, which is the same thing. Right? And what happens if I go across? Well, I have to remember what the to remember what the co-unit is here. So what is the co-unit? The co-unit sends x to 0, which means that it sends x to the n to 0 if n is greater than or equal to 1. But if n is equal to 1, sorry, if n is equal to 0, then x to 0 is 1, and the co-unit sends it to 1, which is the same thing as this. Okay, so this, all of these things agree. And therefore, therefore this is indeed an antipode. Okay.
So what are those? Why'd you circle those on the bottom?
Here I'm just being lazy. So so this is this. I just didn't want to rewrite it. Maybe it takes me longer to explain than to write it. And then here I apply the antipode on the right. And so I meant sum of n choose k, x to the k tensor minus x to the n minus k, which gives me this. Kind of laziness that you can engage in when you write, but not when you think. So if you were writing this, you could probably do this computation and then say, analogously, going down, I get the same thing. But whenever you write analogously, you should actually get your hands dirty on your piece of paper and make sure that it is analogous and it is true. But so it is, yeah. Yeah. Yeah, that's credit worthy to say, do this and say analogously, this holds. And if you ever submit a paper, you can certainly do this and say analogously to that, and the referee is going to be happy with it. The referee might even be happy saying that it's obvious that if you go this way. I mean, actually, if you write a paper, generally you just say, well, obviously this is the antipode. And you know to read behind the lines, but to read between the lines. But anyway, so those are a bunch of examples. Okay, I like examples, but again, I promise you, as much as I can, every single class I'm going to try to do examples, and I'm going to try to do abstraction, and we haven't done much abstraction yet, so let's fly away into abstraction now. So what I want to do now is give you a different point of view on this antipode. When I say different, I mean more abstract. So maybe if you like abstraction for abstraction's sake, maybe you will like this. And if you don't like abstraction for abstraction's sake, then I promise you that we will have a nice consequence that comes out of the abstract machinery. Okay. So I'm going to try to explain to you in a different way what this map S is and why we think of it as a kind of an inverse. So I'm going to do the following thing. Let's say this is kind of a general algebra machinery. So let's say that you have a coalgebra and an algebra. Okay? Which might be on different sets, or the example that we have in mind actually is that we have a Hopf algebra, which has a coalgebra structure and an algebra structure. But to keep them separate, I'm giving them different names. So you just think you have a coalgebra on your right-hand side and an algebra on your left-hand side. And now you're going to consider the linear maps from C to A. Okay? So consider the linear maps from C to A. Okay. I might. One thing you should realize. Generally, this symbol means homomorphisms from here to here. And what kind of homomorphism depends on what kinds of structures you're working with. So for example, if you have two coalgebras, then the homomorphism from C to D might be the set of coalgebra maps, coalgebra homomorphisms. But here we have a coalgebra and an algebra, which are different things, and so we can't ask for these to be algebra homomorphisms. We can't ask them to be coalgebra homomorphisms. But they're both linear spaces, and so we are going to consider the linear maps from here to here. And so what I want to show you is that, and by linear I mean k-linear. So these are coalgebras, a coalgebra and an algebra over the same field. Okay? And sometimes we put a subscript of k here to be more specific, but because there's only one field, I'm not going to write it down. Okay? So I claim that this set, I mean, not only is it a set, it's a vector space. Why? Because if you take two linear maps, you can add them, and you can multiply a linear map by a scalar and get a linear map. So this is a vector space, but I'm going to show you that it's not only a vector space. I'm going to show that it has an algebra structure on it. This has an algebra structure. A natural algebra structure coming from the fact that C is a coalgebra and A is an algebra. And I'm going to show you what that is. So if I want an algebra structure, I mean, as I mentioned, I already have a vector space, right? And so now what I need to do is introduce a multiplication. And the multiplication needs to go from here to here. Right? And there's a long arrow here. And I'm going to show you that there's a natural map going from here to here, but it's useful to put an intermediate object here, which is this one. Okay. And I'm going to define my multiplication map to be the map from here to here, this composite map. Okay. So how does this go? Well, let me first define one side and then the other side. Okay. So let's figure out what this map needs to be. So given a generator here, so you take a pure tensor with an f living here and g living here. Okay, so f is a map from C to A, and g is a map from C to A. Okay. So here, f maps C to A, and g maps C to A. Okay. We're going to get a map here, which I'm also going to call f tensor g, and it needs to be a map from here to here. Right? So what is this map going to do? It's going to take a pure tensor here and send it to what? Well, we know what we should do, right? We should do apply f to the first coordinate and g to the second coordinate. Laziness. I mean, I don't know. If you want.
Yeah, I'm curious what you would, if you were trying to not be lazy, what you would write.
It's not, actually, it's not. So let me repeat the question. So the question is, why do I call these two the same thing? And, well, it's just because I don't want to make a sea of symbols here. First of all, because actually we have been calling this the tensor product of these two maps. If you, I could put a phi here, and then I would have to carry around a phi here. And I just prefer not to. And so, I mean, maybe let me give you a better answer. A better answer is that this is a kind of a natural inclusion here. I mean, we already talked about this tensor map, and it naturally lives in here. So this is actually just an inclusion, and so I don't bother changing the name because I want fewer symbols so I can understand better what's going on. So that's why we do it. But the map is clear, right? I take f and g, and I take their tensor product as maps. Okay. So this is the first map. And now let's do the second map, which goes from here to here. Okay. So given a map alpha from C tensor C to A tensor A, I map it to something from C to A. And what's the natural thing to do here? If I want to go from C to A, right, this is the map that I want to define, and I want to use my coproduct structure on C. So let's bring it in. Okay. Now alpha takes me to A tensor A. And from here to here, I have a multiplication map. Okay. And so I just define beta to be the composite of these, the composition of these three maps. Okay. It's kind of the natural thing to do. And again, as usual, I'm dropping things from the notation so that we don't have an ocean of subscripts and letters. But if I was more careful, I would write a delta C here because this is the coproduct in C, and I would write an M sub A here because this is multiplication of A. Okay. And so here, I mean, I have these two natural maps from here to here and from here to here, and the composite is what I call the multiplication. Now, let me write this a little bit differently in a way that is going to be friendlier to actually compute with. So the multiplication of f and g, we're actually going to call yep.
Just trying to make sense of what's going on the right-hand side there.
Mm-hmm.
We're trying to find a function. It takes an alpha and gives us a beta. We've drawn this diagram to sort of say what we want that function to do,
Mm-hmm.
but we're actually asserting its existence at the same time. We're saying there is a beta such there is a beta. Yeah, there is a beta such that diagram.
That's right. So I'm trying to define a map from here to here. And so what I do is I say, given alpha here, what do I need beta to be? And I'm saying beta should be the diagram that makes this commute. And in this case, it's obvious that it exists because beta is just the composition of this, this, and this. Sometimes it's not obvious that you can make a diagram commute. But here, this actually gives me a definition. Beta is the composite of these three maps. Okay. And then I'm asserting that this is linear from alpha to beta. But again, everything that we have written down here is linear, and so that's for free. Okay. So let me write in formulas. Maybe now you're going to be grateful for Sweetler notation, because this looks a lot nicer in Sweetler notation. We have F and G that go from C to A, and now their product we're denoting like this. Okay? And what does this product do? Well, in order to say what it does, I evaluate it at some C. Okay? And what am I doing? Well, like I said, this is just the canonical inclusion, and so there's nothing really happening from here to here. This is really where the action takes place. So I'm saying take your element C, little c, it lives here. Apply the coproduct. Okay? And so I'm slowly going to build a formula. It's not right, it's not correct. What I'm writing right now is not correct, but it will be. What I'm going to do is just travel around this map and change the formula step by step. So I take my C. I apply delta, and so I get this in Sweetler notation. Okay? Now I apply alpha to that, and so what alpha does is that it applies f to the first coordinate, g to the second coordinate, and I multiply. And so what I get is this. Okay? And so in Sweetler notation, this is actually very nice and simple. This is how you multiply in Hom of C comma A. And this is called the convolution product.
This is the same product that we saw in
So in the incidence algebra, there's also a convolution product, and
yeah, that's it. Because
it must be the same thing, but yeah, because if C happens to be the coalgebra of posets, then remember that the coproduct is take your poset and cut it in two, and apply something to the bottom and something to the top. That's exactly what we're doing here. So that's convolution, but at that more general level. Okay. So that is the multiplication on this algebra. Okay. And in order to have an algebra, I also need a unit. So this is multiplication. But I also need a unit. And there's a couple of ways of talking about what a unit is, but one thing that you can do is just to say what is the element that you're going to call 1 in Hom of C A. So you need to decide what 1 should be in Hom of C A. So you want to define some map from C to A that is so nice and special that you want to call it 1. Okay? So can you think of a very nice simple map from C to A? And again, keep in mind that you want to use the fact that C is a coalgebra and A is an algebra. So how do we go from C to A? The coalgebra wants to send C to K and the algebra wants to send k to A. Right? This is the co-unit of C, epsilon sub C, but I dropped the subscript because there's only one epsilon here. And from k to A, I have the units. So I get a map from C to A, and I call that 1. Okay? That's my... Now, maybe... So let me say that this is the map U epsilon, right? The composition of U and epsilon, and that is what I call the 1 here. So the 1 of Hom CA is the map U epsilon. Okay. All right. Okay, so what does this have to do with anything? Well, what we're going to do is now yeah, so I guess really there's two U's, because there's the U of A and the U of Hom CA, which is given by this one. But anyway, what I mean here is UA, and what I mean here is epsilon C. Okay, so now let's do the following. Let H be a Hopf algebra. No, let H be a bialgebra, sorry. And let HC be the coalgebra, and let HA be the algebra. Okay. So here, I mean, forget that you can multiply and have a unit, and here, forget that you can co-multiply and have a co-unit. And let's consider Hom of HC, HA. Okay? Now, let me make an observation that there is a very natural map here. There's a very natural linear map from here to here, which is the identity. Right? Because as far as vector spaces, this is just the identity sending you here to here. Okay? And so the claim that I want to make is the following. In a bialgebra, a linear function is an antipode for the bialgebra H if and only if S is a two-sided inverse of I in Hom of HC, HA. Okay, question?
So wait, I know it sounds it's going to be a dumb question, but what is this I again?
So I is the identity function. Now the thing is that these two things sound like they're different, right? But remember that their ground set is the same. Their ground set is H here and H here. It's just that here I'm considering this with a coalgebra structure, and here I'm considering this with an algebra structure. But as vector spaces, they're the same. And so this is just the identity map on the vector spaces. Okay? And so what I'm claiming is that a linear function s from h to h, which if you want to be more careful, you would say that it goes from hc to ha, right? So that it actually lives here. It's going to be an antipode if and only if it's an inverse for this guy. Okay? In this funny algebra. And this one is the one of the algebra, which is that one. So maybe what I should write is in Hom of HC, HA. Okay? And so this is another way of defining the antipode, and actually some books do this. Some books just say, consider this algebra structure on Hom of HCHA, and then they say an antipode is an inverse of I, a two-sided inverse of I. Okay? And again, depending on whether you like abstraction or not, you might or might not be too excited about this. But one very nice thing about this is a corollary, that if S exists, it's unique, which answers your question. If S exists, it is unique. In other words, a bialgebra has either no Hopf algebra structure or one unique Hopf algebra structure. And the proof is very easy. It's just, if you had S and S prime were antipodes, then just compute in Hom CA. Let's compute this. Okay. This is 1 because S prime is an antipode. So this is equal to S. And this is 1 because S is an antipode, and this is equal to S prime. Mm-hmm. That's right. So S, I, and 1 are all maps in here.
And 1 would appear to be a map that doesn't do anything, which would make you think that it's equal to I. So I'm a little
Yeah, so I see your confusion that it sounds like 1 and I should be the same thing, but it turns out they're not. And one reason they're not is this. So they're not. If you look very carefully at what 1 is and what I is, they're different. So I is the identity map from H to H, and 1 is the unit in that. And if you kind of write down what they are, you'll see that they're different. Yeah?
Well, in particular, Q is not generally surjective from K to A, right? Usually we consider K to be embedded in A. Whereas
Yeah, I mean,
one should be an isomorphism, or I should be an isomorphism.
that's right. So this is a much simpler map. It's a pretty trivial map because you take C, which is presumably some big Hopf algebra, and you collapse it to just a field, which is tiny. Okay, and then from the field you go to something. And so as vector spaces, this has at most dimension 1. The image has at most dimension 1, whereas that's an isomorphism.
But then if we're losing information, how is 1 times something always the same thing? Why aren't we losing information there?
So I guess what
Why aren't we getting something like restriction of S?
I guess what I should have done is say check that this is really check that this is really 1, which it is, and you just have to check it. Now, I feel like the video probably ended already, and maybe it's not telling me. I just need to justify this proposition for you, but actually this proposition is almost empty. And so, just so you practice with the notation, you should write down what this equality is. Okay, because You just have to unravel what all these maps were, and you get a formula here. Actually, I mean, the formula is this one, right? Sum of S of this times identity of this is equal to something is equal to something. You can write down in Swiller notation what this means using this. And you can also write down in Swiller notation what this means. And when you do that, you'll see that they're exactly the same thing. Okay? And so actually that's a very easy proposition when it comes to writing it down. The difficulty is just kind of unraveling the notation, but there's really very little content here. Okay? And that's it. So that proves the fact that antipodes are unique if they happen to exist. Okay? All right.